Hello, my name is Majori, and welcome to Lab 5, Fallen Slinky. And hopefully you like my double entendre of the fall PowerPoint theme that goes with the Fallen Slinky. You can just call me J. Cole at this point. So the main purpose of this lab is to predict the motion of a fallen slinky and analyze the effects that the surroundings have on it. And as always, I'm going to be using Tracker to track the observed position and GlowScript to create the computational model. And the ultimate goal is to determine whether the bottom of the slinky stays stationary in the computational model and to compare that with the tracker data. And just the result, what we're going to see is that although there are some fluctuations between the observed and the predicted positions, the bottom of the slinky will remain stationary. Alright, so what fundamental physics principles will we be using in this lab? Well, just like the previous four labs, we're going to be using Newton's second law, aka the momentum principle. You can literally just rename this course to Applications of the Momentum Principle. Alright, so what this says is that the system's change in momentum is proportional to the net force applied. And here's the equation for that, and we can basically gain the velocity update and the position update formula by just rearranging some of the variables. Next up, we're going to use the drag force, which is the resistance force caused by the motion of a body through, say, air. And here's the equation for that. And finally, we're going to be using the gravitational and the slinky or tension force. And the gravitational force is, of course, mass times gravity. And the slinky force is just another word of saying the tension force, and it's going to be opposite of that to gravity. For the observed motion, we're going to be using this video from Veritasium's channel. The mass of the Slinky is 0.218 kilograms. For calibration purposes, Derek's height is 1.75 meters. Initial position is as such, and initial velocity is 0 since it's dropped from rest. Alright, and now it's time to make the code for the computational model. Now, first thing we're going to do is set all the initial conditions, and most of these were gained from the tracker analysis, such as spring mass, the initial position, the initial velocity, and the drag proportionality constant. Now, this constant just makes the drag force equation work for this lab, and it's generated through trial and error. So the computational model is going to be split up into two main parts. The first part is where the bottom of the slinky remains stationary. Now, during this time frame, we want to understand what's going on with the bottom of the slinky. We want to analyze its motion. So let's use the velocity update and the position update formula. Well, in order to use this, we need to know what's going on with the net force. Well, since the bottom of the slinky is stationary, net force should be 0. And let's just establish our system and surrounding just to get a better understanding of this. Our system is just the slinky itself, and the surroundings is everything else, such as the Earth. So the Earth is going to be adding a downward force on the slinky, but the slinky, since it's stationary, should have an equal but opposite force going upwards, known as the tension force. Alright, so what we should theoretically be seeing through the computational model of the first while loop is that the slinky's position remains constant since the net force is always 0 during that time frame. Now, what happens when the slinky starts falling down? When the top reaches the bottom and it's now starting to fall down, it's not stationary anymore. Now, the net force is not going to be 0. In this case, we're still going to have the force of gravity acting downwards, but now we're also going to have a drag force, which again is proportional to the velocity of the slinky squared. Now we're going to do the same thing. We're going to use the position update and the velocity update formula in order to track its position over time. Here's our beautiful graph showing the observed versus predicted position of the bottom of the slinky, and this was generated using data from the observed tracker model as well as the computational model. Now, as we can see, the computational model does a great job at replicating what's going on in the real world. However, there are some fluctuations. And one possible source of error is that the observed motion experiences fluctuations due to external forces, such as the wind, that is not accounted by the computational model. Next up, there's always going to be some human error, such as inaccurate tracking point placement. Alright, let's take it a step further and take a deeper dive into the results. So, why does the bottom of the slinky remain stationary in the first place? Well, as stated before, the forces in the y direction cancel out. Although we do have gravitational force acting downwards, the slinky acts as a big spring and counteracts that force with a tensional force that's equal and opposite. Now, next up, what if we put a large weight, say a tennis ball, at the bottom of the slinky? Would it remain stationary? Well, this depends on the slinky itself. As long as we have a slinky that is either long enough or has a large enough spring constant so that the tension force balances out with the gravitational force, the tennis ball or the weight will remain stationary until the top of the spring reaches the bottom. As always, thank you very much for your attention. This is going to be the final Physics 1 lab, and I hope to see you next year in Physics 2.